Section 3.5.1, Displacement Transmissibility Solution for Base Excitation. We want to talk about transmissibility, which is how force moves from the base into the system that we're interested in. Here, it's the mass, right? So you can think about this as something like I have a wheel, and to that wheel, I have attached my beautiful shock system, which is made up of these two idealized components, and then I've got my my one-wheel car up here, right? And I want to know if I put 1 centimeter of displacement here, how much does my car move, right? If I'm riding in a car, I probably want 0 centimeters or the lowest possible amount, right? Maybe if I've got a rock crusher or something like that, I want to put 1 centimeter in and get 10 centimeters out, right? So that's displacement transmissibility. How do I transmit displacement through my spring and my damper? The steady state solution is really more important than the transient solution when designing systems for continuous use. The transient solutions are going to die out. The steady state solutions are going to be there. You'll always have new transients being added, but the steady state solution is going to be there consistently. So the particular solution for a base excited system with the equation of motion that we just wrote out in the previous section is still x of p. And we can call that x of p of t. And because it is a linear system and everything we do in this class is linear, a sum of 2 solutions is a solution. So I can say that x of particular 1, not squared, just x solution 1, I put it in brackets so you know it's not squared, sorry, it's not an exponent, plus x particular 2, so that one's not squared. Both of these are the function of t, can mathematically represent my solution because, again, I'm dealing with linear solutions, right? So recall that the steady state solution of a harmonically excited spring mass damper can be expressed as xp of t is equal to capital X cosine of omega t minus phi p. So for a base excitation system, right, we can convert that expression a little bit because I also have a phi now in my base. So I'm going to convert that to x of p of t is equal to capital X cosine of omega b, so that's the frequency of my base, multiplied by my time minus phi subscript 1, because it's going to be the first part of my particular solution. This is where we get into the applied mathematics, right? We know that it's a linear solution. We know that we can make a solution by a set of solutions, and we're just throwing things in now that we hope will level out at the end. I promise you they'll level out at the end. Very smart people have worked on this and developed it. But if it seems a little bit ad hoc, it's totally understandable. We're just kind of throwing things in that all cancel out at the end. All right, so if we drop the terms, okay, so we had an arbitrary forcing function from before. Remember that we had c cosine of omega bt plus, I think I had blue, d sine of omega bt equals to x of p, which is our particular solution, which is equal to x of p1 plus x of p2. which is what we've defined for our solution because we're dealing with linear systems and we know we can break it apart. Now I need something for x of p1 and x of p2. If I drop the t's, the subscript or the parenthesis t's just for simplicity, I can go x of p1 is equal to capital X, but it's of 1 because it's for my first solution, cosine of omega b t minus phi 1. All right. And now I can have my second side, which is x of p2 equals capital X of 2 sine of omega bt minus phi 1, which seems weird, right? I've got a phi 1 in the top one, and I've got a phi 2 in the bottom one. So x of p1 uses a cosine term, and x of p uses a sine term. Both solutions use phi 1 as the damping term of the phase angle is independent of the excitation out amplitude, right? And so the sine and cosine here naturally account for our difference in phase between the two. So I've already got a difference in phase between the two with my sine and my cosine. And so I'm going to tie them together with phi 1 so I can get things to cancel out. So if we use the method of undetermined coefficients to obtain a solution for x of 1, that can be as simple as setting 2 zeta omega n omega b y equal to f naught. We can get a driving forcing function that looks like this. And we're not going to walk through the method of undetermined coefficients here, but you can do that if you so desire. I don't know why you would, but that's where it comes from. And we have a pretty long division here, so draw a nice long line if you can. We have 2 zeta omega n omega b capital Y over a pretty long radical. Maybe I'm overselling how long it is, but that keeps it clean. And our good friend, omega n squared minus omega b squared plus 2 zeta omega n omega b squared. This whole thing needs to be multiplied by something that oscillates. So we have cosine of omega b t minus phi 1. And now I need a solution for phi 1. And if I use my trigonomic angle again, that triangle that we did in the first couple weeks of the class, I can get phi 1 is equal to tangent inverse of 2 zeta omega n omega b over omega n squared minus omega b squared. And that gives me my phase angle. But this only gives me a solution for xp of 1. So I need a solution for xp of 2. And we can use the exact same methods here for undetermined coefficients. Set things from setting f0, setting f0 for our forcing function. We can get xp of 2 is equal to, it's going to be pretty much the exact same expression, but we have a different numerator. And we have omega n squared, capital Y. And then we're going to have the exact same denominator. Whoop. Omega n squared minus omega b squared. That whole term squared. Plus 2 zeta omega n omega b, that whole term squared. And now we're going to have sine of omega b t minus phi 1. So we have a very long expression here that makes a particular solution for displacement transmissibility, right? Again, we know we defined our own terms here. So we are the masters of our own destiny. We have x of p is equal to xp of 1 plus xp of 2. I've got a common denominator. So I can use that to combine some terms here. I'm going to get capital X of P is equal to omega n capital Y, because I have those in both of my terms. And then I have a very large square root with a division in it. And on top, I have omega n squared plus 2 zeta omega b, and that whole term is squared, divided by the denominator that we had before. Omega n, our natural frequency squared, minus omega b, which is the frequency that our base is moving at, that term squared, that whole term squared, plus 2, the critical damping ratio of our system, omega n, the natural frequency of our system, omega b, the frequency that our base is moving at, that whole term squared. Now I hit an issue. I have a sine term and I have a cosine term, and I want to merge the two. The only thing that's different between sine and cosine is they're out of phase, right? So I can add a phase term in here to accommodate for the adding of my sine and my cosine. So that means what I can end up with is I just get cosine, even though I have sine and cosine above. I get cosine, open parenthesis, of omega bt minus phi 1, which they both have, but there's got to be some other phase that's disconnecting the two. So I go minus phi 2, and by just adding that in, I can link my two sine and cosine into having just a cosine function. If I put this back into my trigonomic functions, I can get that phi 2 is equal to our tangent negative 1 of omega n over 2 zeta omega b, and that's my solution for my omega b. Again, I'm not actually, you can solve this out for any specific point in time t. right? That gives you X of P, you have a particular solution. You could figure out where your mass is for any point in time T, but that's not really what we're interested in design, right? We're interested in the transmissibility and how forces move through it. Again, we can always talk about this in terms of damping and stiffness, but it's really a game that we're playing between the ratio of our driving frequency and the natural frequency of the system, right? So we can go back and define or redefine or reuse, however you want to say it, omega b over omega n is our good friend r. Before we had omega over omega n, right? Because omega was our forcing function from the side. Now we have a damping, sorry, a base forcing function. And so we have omega b on top. And this is the ratio that we care about. Into the temporal response, we can rearrange, we can stick r back into this equation, and we can get rid of a lot of these omegas. Everyone agree with that, right? So I can rewrite this equation without any omegas, and that's going to give me capital X is equal to y times the square root of 1 plus 2 zeta r squared, and that's divided by 1 minus r squared. Oh, sorry, 1 minus r squared, that whole term squared, plus 2 zeta r, and that whole term squared. Okay, so that works. The problem here is I get my displacement, right? But actually what I would like to be able to do is just plot a normalized displacement for any given input on like the left-hand side, so then I can plot a normalized plot. So if I move my y over, I get a very common function. So if you don't write much down, write this one down. X over y is the square root of what we had before. And that's 1 plus 2 zeta r, that whole term squared, 1 minus r squared plus 2 zeta r, that whole term squared. Okay, this means that we have an expression that we can plot out for different factors of r, right? So r, again, is our omega b over omega n. So that's r. And then here we have our displacement ratio, which is, let's go x over y. And that's how much I displace for how much I put in, right? So a 1-to-1 would mean I put in 1 and I displace 1. And let's get a couple values here. 0, 1, 2, 3, 4, and 5. So 0, 1, 2, 3, 4, and 5. So 1 here means I put in 1 unit, 1 millimeter at my base, and I get 1 movement of my mass, 1 millimeter of my mass.
What does that mean? You move your base by like 1 centimeter up, your mass will.
Yes. So if I move my mass, if I input my base, my y, maybe I'll redraw this here. Again, we have this function. I have my base. I have my y moving up. My stiffness, K, it's a beautiful spring. Damping, C. I have my mass, and I have x positive and up, right? So if I move y up 1 millimeter, x goes up 1 millimeter when I have a displacement ratio of 1. And then I have my frequency ratio here. And that's R. And let's go 0, 0.5, 1, 1.5, 2, 2.5. Okay. And again, this is going to be normalized based on my damping. So let's just say I've got zeta equals to 0.1. So I have a system that doesn't have a lot of damping, right? It's a pretty soft system, might be another way to describe that. I know that I'm going to get a pretty good resonance at 1 because I've got a system without a lot of damping. And so it just happens to be there. I start at 1. And then I come down like that, right? So I get a lot of damping, and then I come a bit lower. Let's redo that one. I come a bit lower, almost down to 0 when I have a low amount of damping. Vice versa, if I have a very stiff amount of damping, so let's go red, let's go zeta is equal to 2. So I'm a very stiff system, right? I am over damped. I'm going to start at 1. And maybe I just drop down just a bit. I don't ever go above 1, right? This means if I have a metal rod, right, and I put in 1 millimeter of displacement at one side, what do I get out at the other side? 1 millimeter, right? And it doesn't matter the ratio of what that natural frequency is. I'm pretty much always going to get out of it what I put in, which makes sense. If you think about things that are stiff, right, you get out of it what you put in. You don't ever get more out of the backside, but you don't ever get less out of the backside. If you think about something that's soft, right, at 1, when I'm at resonance, I get a lot more out of the top of my system here, my mass, when I'm exciting it from the base. But if I were to be able to come way out here on my soft system, I can actually be putting in a fair amount of energy and getting almost nothing out, right? And it's just getting it to oscillate at those right frequencies. So that's where you get vibration isolation or a sink or a well. It can be called a vibration sink or a vibration well. And you might want to operate a system at a frequency where you can put a lot of displacement in and you don't actually get a lot of displacement out. So let's fill in a few in between. I've got zeta is equal to 0.25. And just like before, I'm going to come up here and I'm going to peak from there. And you'll notice that my peak and my peak is moving leftwards. And if I have another one, go gray, of zeta is equal to 0.5, I'm actually going to peak at about 0.75. And then I'm going to come out here like that. And what you can see here is that I am slowly getting, just like before, I have my peak values following this line, but now I have a very other interesting point here, which is where they all cross, right? And that value is R is equal to the square root of 2. And that's where they flip from overdamped systems having a greater response to underdamped systems having a greater response. And it's also where they flip back through 1. If it's not super clear, this here, x over y is equal to 1. So what does this mean? From a design standpoint, if you have an underdamped system, which most of the time you will have, and you want to limit displacement transmissibility, you want to operate at a base excitation frequency that is greater than R equals the square root of 2, right? If you have a, well, that's pretty much it, right? If you have an overdamped system and it's really overdamped, you pretty much always just get 1 out of 1, right? It goes down a bit at the end, but you're not gaining a ton. If you have a underdamped system where you want to get more out of it in terms of displacement, where you put in like a shaker or a concrete vibrator or something like that, you want to run at a frequency ratio R, which again is R is equal to omega B over omega n. You want to run that less than the square root of 2. And the less damping you have, right, the more vibrations that you will get. And again, if you had absolutely no damping, which wouldn't happen, but let's say that you really wanted to have absolute no damping, you would have a system that looks like that, right? So it would be open, it would be in resonance, and then as you get farther and farther out, it would eventually, go to 0. Technically, all of these go to 0 at a frequency, but only works for a linear 1 degree of freedom system.